A lot of people have an idea of the church's sense of astronomy as being geocentric, that the Earth is at the center, that somehow human beings are at the center, that we're the most important thing in the universe, and that the church didn't want to give that up. That's not really what the church ever taught, and certainly not what the church teaches today. If you look at this medieval view of the universe, yes, you can see the Earth at what seems to be the center, but you look carefully, it's surrounded by rings, which are the planets. The planets themselves are thought to be the realms of different ranks of angels, and as you go further and further out, you eventually get to the realm of God. What they observed, being good astronomers, was that the planets moved in a regular pattern that never quits. And they thought, quite reasonably, there must be a different kind of physics out there than down here. Because down here, things eventually grow old and stop. Up there, things move forever. That means that the Earth was not the center of the universe in this model. The Earth was the bottom of the universe. It was the lowest place, and the only place lower would be the center of the Earth where there was fire and brimstone, clearly hell. And if you don't think there's fire and brimstone, let me take you to the island of Volcano where I can show you the fire and brimstone visible through a hole in the Earth's crust. It was good science. It was able to predict what they saw, and it was able to explain the things it predicted. C.S. Lewis, writing about it in a marvelous book that I would recommend to anyone interested in that medieval cosmology called The Discarded Image, he says it was, to his mind, one of the most beautiful and eloquent descriptions, one of the greatest creations of the human imagination. It only had one flaw. It wasn't true. But notice, in this picture, the world is round. I mean, how many people here were taught by their teachers when they were kids that Christopher Columbus proved the world was round? Utter nonsense. Because they knew the world was round. And besides, Christopher Columbus didn't make it around anyway. How did he prove anything? Once it was understood that the universe is more complicated than this, it was priests who were in the forefront of exploring the new universe. This is a map of the moon made by two Jesuit priests in 1651. That's less than 20 years after the Galileo trial. And yet they made this map with their telescopes and invented the nomenclature that we still use today. Notice, for instance, that the craters are named for famous scientists, and the most prominent crater on the moon, they named Crater Copernicus, 20 years after the Galileo trial. The other craters in that part of the sky, Aristarchus, Kepler, Galileo, were named for other people who believed that the sun, not the earth, was the center of motion. Incidentally, they named two craters for themselves in that part of the sky. Was it a hidden message? Who knows? There are now 35 craters named for Jesuits. It helps if it's a Jesuit making the map. Jesuits were involved in astronomy throughout the period of after the telescope was invented. By the time of the first transit of Venus, it's estimated that they ran 1/4 of the observatories in Europe. In spite of that, you will still find books, mostly written in the English language, saying that all astronomy in the Catholic South stopped and only astronomy took place in England. That's what the English would like you to believe. The Irish half of me is kind of about that, but nonetheless, the idea that science and religion are at war with each other really only comes up in the end of the 19th century. That's when the books are first written saying that it was the evil Catholic Church who thought the world was flat and tried to stop Christopher Columbus from sailing around the world. That's where they create the myth of the war between science and religion. But if you read those books carefully, what they really were tracts to make sure that people with vowels at the end of their names didn't come into America and pollute our precious bodily fluids. It was anti-immigration fervor that fueled the idea that the Catholic Church was against science. In order to counter that, in 1891, Pope Leo XIII decided to found a specific observatory funded by the Vatican so that the world would see that the Church supports science. And incidentally, the world would also see that the Vatican was a nation independent of Italy, which had its own national observatory. They chose astronomy simply because there had already been great Jesuit astronomers who had built up the reputation of the Holy See in doing astronomy. Most lovely, the Pope's coat of arms had a comet in it, just by coincidence, which was kind of nice. The original telescopes were on the wall of the Vatican by the 1930s, when the Concordat with Italy was signed, and the Vatican's summer home at Castel Gandolfo was restored to the papacy. Pope Pius XI built 2 telescopes, which can be seen to this day on the Papal Palace. And those telescopes were the home of the Vatican Observatory for the next 70-so years. These are the papal quarters. That's where Pope Emeritus Benedict is living right now. That used to be my office. I was one of the few people in the Catholic Church above the Pope. Besides the theological sense of showing that we're not anti-science, why should we be science? The Church invented science. There is a deeper reason why the Church embraces science, and that's seen on the walls of one of these telescopes itself, this marvelous plaque put up by Pius XI with the phrase, Deum Creatorum Venite Adoremus. And even those who are post-Vatican II babies should be able to do this Latin. Deum, God, Creatorum, the Creator, Venite adoremus. Oh, come, let us adore him. God is the creator of the universe. God expresses himself to us creatures in the things he has created. That's not me saying that. That's a quote direct from St. Paul, letter to the Romans, chapter 1, verse 20. The only verse I know because I'm a Catholic. And for 75 years, we actually physically lived in that same building and had our offices there. In 2009, we were given new offices. It sounds like, oh, we were kicked out of the palace. The palace was beautiful, but the palace was 500 years old, not designed with the internet in mind, not heated very well in the winter, not cooled at all in the summer, and none of the plugs were the same. So instead, we had to move to the miserable gardens here. Tough life. You can see in the foreground the olive trees. They have fresh squeezed olive oil every October. Behind it is the helipad. That's where Benedict landed a week ago. Beyond that, a series of trees, and behind the trees is where our quarters are. That's incidentally the Mediterranean you see off in the distance. So these are our quarters. And when we moved in, they spent 2 years and an enormous amount of effort giving us the most beautiful quarters you could imagine. When we moved in, the landlord himself came to show off the place. He's holding a Mars rock, a meteorite that we believe comes from Mars. This picture ran on the front page of the L'Osservatore Romano. And when it did, I called my mom immediately and said, I'm on the front page of the L'Osservatore Romano. You see the little stripe of black to the far right there? That's me. And here's the picture to prove it really is me. That's him taking the picture you just saw. So that's the observatory. Why am I involved? Part of it is just being born in the right place at the right time. I was a Sputnik kid. I was in kindergarten when the first satellite was put around the Earth. And, you know, NASA said rockets were blowing up, so that's me trying to explain to NASA what they were doing wrong. As all little boys of that era, sadly not girls, boys, I was told, if you're going to be smart, you're going to be a scientist. And I went to a Jesuit high school. I learned Latin and Greek there instead, because that's what the smart kids did. And did a couple of detours, but by my sophomore year, I had transferred out of a history program at Boston College to MIT. I went to MIT for 3 very serious reasons. And you recognize that your career is controlled by the whims of a 17-year-old, namely you at that age. MIT had weekend movies, pinball machines, and the world's largest collection of science fiction. That was me without a beard. Yes, it was the 70s. I was class of 74. And that's where I learned planetary science. I went on to the University of Arizona. That's me at the University of Arizona. 9-to-1 male-female ratio. You can find the 1 if you look real hard. This was the first class of planetary scientists in the first department in the world dedicated only to studying the geology and astronomy of planets. And in that collection of characters are a number of rather outstanding people. The guy with the wild hair behind me is a fellow named Cliff Stoll, became famous in the 80s, wrote a book called The Cuckoo's Egg, and worked out basically the book that explained the internet to an entire generation of people, as he describes how he caught a Soviet hacker breaking into his computers. The fellow behind me and immediately to my left, sitting down, John Grady, was one of the real pioneers in understanding asteroids and asteroid astronomy. And the fellow sitting behind him is just retired as the curator of the moon samples of the Johnson Space Center. So we all did pretty well. The one woman was Martha Leake. She was the first of us to get tenure, so she was obviously doing something right. I had this passion for astronomy. I had thought maybe of being a Jesuit in my younger days and decided not to. But this passion for astronomy carried me through graduate school. And after graduate school, I got a postdoctoral fellowship at Harvard College Observatory. And when that ran out, at MIT. To someone who doesn't know, that sounds pretty good. You know, you're in the big leagues. You're doing major research at Harvard and MIT. To someone in the field, they hear, 5 years as a postdoc, couldn't get a job, could you? And that's what I was feeling. At that point, I'm pushing 30 years old. 30 years old, no chance of a serious job in sight. And that Jesuit education had ruined me in one sense. Because I'd lie in bed at night thinking, why am I wasting my time doing astronomy? People are starving in the world. Isn't there something more worthwhile I could be doing with my life? Who gives a hoot about the moons of Jupiter? Why am I putting so much effort into this utterly useless activity? Plus, I'm turning 30, I'm getting old. Oh my gosh, I'm getting old. I'm 60 now, by the way. So, I didn't have an answer. And I decided there's no problem so big you can't run away from it. I decided to join the Peace Corps. I could be doing something adventurous before it was too late. I could go and see the world, and maybe I could do something worthwhile for people. So I signed up, joined the Peace Corps. They sent me to Kenya. I said, I'll go anywhere you ask me to go. I'll do anything you ask me to do. And they thought this was great, and I was full of enthusiasm. And then I spent 8 weeks in culture and language training, living in mud huts in the middle of nowhere, upcountry, Kenya. And I realized why I hadn't done this before. I am not an adventuresome person. My idea of a great vacation is to sit at home and read a book, preferably science fiction. Adventures are things that should happen to other people in books, not to me. And what was worse, I was homesick. I was really homesick. I was incredibly homesick. Homesick to the point where I was physically ill. I couldn't keep my food down. My stomach was tied up in knots. I was not able to function anymore. I was suddenly, had forgot all my Swahili, and the trainers realized there was something wrong, and they pulled me out of class, and they put me back in a place where we'd been doing some training, but I was by myself. I'm lying in bed, and I said, you know, this isn't me. I can't do it. I can't do it. I've got to go home. I'll tell them tomorrow they'll send me home. But if I'm going home tomorrow, tonight is going to be my last chance to see the Southern Cross. Always wanted to see the Southern Cross. Those constellations that you can only see from the equator or further south. And I had this book that I'd had since the 5th grade called The Stars, A New Way to See Them by H.A. Ray. Fantastic book. If you want astronomy, get this book. And you don't have to be in the 5th grade. Get it if you're 60 years old. I still have a copy of it. It teaches you how to find the constellations. And it had a whole section of constellations in the south. So I pull out the book and they say, sure enough, at 5 in the morning, if you get up, you should be able to see the Southern Cross. So I got up. And I looked to the south. And I don't know if you can see, off to the left, there are 2 bright stars right above that tree, Alpha and Beta Centauri. And keep going, and there's that little kite shape, or diamond of stars, the Southern Cross. And it was beautiful. It was one of the prettiest things I'd ever seen. But then looking further, I saw, wait a minute, if you go up there, that's Sirius, that's Orion. I know Orion. And I looked to the north, that very same moment, there's the Big Dipper. There's Leo the Lion, upside down, looks kind of funny, but I know him. And there's Gemini the twins. In fact, at that moment, 15 of the 20 brightest stars all happened to be visible, along with Jupiter. And I thought, this is beautiful. I'm home. I am home. Any place where I can see the stars, I'm home. I don't have to go back to Michigan to be home. This is a pretty nice place. I think I'll stay here. And I stayed there. They first assigned me to a rural school where there was no black on the blackboards, no windows in the windows. Before I even got there, they changed their mind and assigned me to a national school. I wound up being at a school supported by the Save the Children Foundation that had its own building for its computer lab. This is 1983. And lasers at the students doing A-level, really bright students. And I was there for 3 months before I was at the University of Nairobi teaching graduate students, teaching them astronomy. The very thing I thought they didn't need. And I was curious because, you know, I was worried about people starving in the world, and yeah, people were starving in Africa, but one of the things I learned living and seeing my friends upcountry, that these are people who live close to nature. And there's a word for people who live close to nature, and that's starving. Because for all of the problems that technology gives us, pollution, alienation, a sense of separation between you and nature, all of these things are real problems. All of these things are things you have to confront. Nonetheless, a technologically sophisticated society is the only society we know that can regularly feed its people. And to have a technologically sophisticated society, you have to have a technically literate populace. For that, you have to have schools. For schools, you have to have teachers. For teachers, you have to have a teacher's college. The kids I was teaching in my graduate school classes had jobs waiting for them at the Kenya Science Teachers College. To teach the teachers, to teach the kids, so that someday the country could feed itself. And that's why they needed astronomy. But that's not why they wanted astronomy. Because I went there with a little telescope, and all my friends who were living up country where there was no black on the blackboards and no windows in the windows said, come on up, bring your telescope. And I would set the telescope in every village, and everybody in the village would come out and look through the telescope, and they'd see the rings of Saturn and go, wow! And they'd see the craters on the moon, and they'd go, wow! And they'd see the nebulae in Scorpius, and they'd go, wow! Now, at that time I had a cat. I had a really clever cat, but my cat never asked to look through the telescope. My cat also never said, wow. Cats are like that. Looking through a telescope and being amazed is something that's the same whether you're in Kenya or Michigan. It's something that human beings do. Wondering about who are we and what are those stars and how do we fit into it all. And learning that as part of the human race, we actually went to the moon. We actually are putting people in orbit. And we, human beings, the entire human race is doing that. Not only the astronauts, not only the engineers who built the equipment that the astronauts use, not only the people who taught the engineers who built the equipment, or the people who fed the people who taught the engineers. Our entire human civilization was involved in putting people on the moon. The thing that we will be remembered for in 100 years' time or 1,000 years' time. Back when people have forgotten what the Vietnam War was all about. Back when people have forgotten who the president was. Everybody remembers Galileo, right? You all remember he got in trouble with the Pope? How many people here know the name of the Pope? How many people here know what was going on in the world at that time? Something called the 30 Years' War, which made World War II look like a pop gun. Who can remember who was even fighting in the 30 Years' War, much less the names of any of the generals? We remember Galileo. In 50 or 100 years' time, we will remember Neil Armstrong, long after all those other people have been forgotten. And this is something that the entire human race did. And to deny someone the ability to participate in that very human activity, because they were born in the wrong continent, because they were born with the wrong income, because they were born with the wrong gender, that is to deny them their humanity. But to give them astronomy gives them a part in the human adventure of our generation. And that's why they wanted astronomy. They taught me that. And I went home and wrote a book about how you can find things in a telescope. I went back and taught at Lafayette College and discovered that I loved teaching. I loved being at Lafayette. But I missed what I had in the Peace Corps, which was standing for something bigger than myself. So at the ripe old age of 37, I entered the Jesuits. At the ripe old age of 39, I took vows. I studied a couple of years at Loyola University in Chicago, and then trying to figure out which Jesuit university I was likely to teach at, I got a phone call from the director of formation who said, "Stop looking, we just got a letter from Father General himself assigning you to the Vatican Observatory." First I'd heard about it. Now, you take these vows, right? Poverty, I was used to that. I'd been a grad student. Chastity, I was used to that. I'd been a grad student. Obedience, I was not used to. I'd been a grad student. But under obedience, I had to go to this miserable place, live in that awful palace, look at this terrible scenery, eat that horrible Italian food, and oh yes, do whatever research I wanted to do. The director gave me very strict instructions. Do good science. And it was up to me to decide what science to do. I discovered that they have one of the world's largest meteorite collections, and I've been working on that ever since. Just this past year, this is my new meteorite lab that's been built in the Papal Gardens, wonderfully equipped to do the kind of research I'm involved in. And the Vatican not only supports me with a wonderful lab, they've even loaned me this German professor to help out. Since this is my real passion, is to talk about the meteorites. These are rocks from space. They're chips off the asteroid belt. They're things that are 4.5 billion years old. They're telling us what happened when the planets were being formed. What do? I measure their physical properties. I try to see how they're actually physically put together. One of the questions that I had asked, which no one had really figured out a good way to do, was to measure their density and porosity. Now, what's density? That's mass divided by volume. You know, Christmas morning, when we were kids, we were allowed to open one present before going to Mass. So you wanted to make sure it was a good one. You didn't want it to be a box of socks. How do you pick up the box? You feel its heft for its volume. You're measuring its density. Density is mass divided by volume. Mass is easy to measure, put it on a scale. Volume is really hard because these are very irregularly shaped rocks. Now, you may all know the story of Archimedes. I knew it began with an A. Asimov, one of those guys. If it had been a meteorite, I would have remembered. Dunk it in water, see how much water comes out. You're not going to dunk my meteorites in water. Water's going to hurt them. Worse than that, water will get partly into the cracks, so you don't know, am I measuring the outside shape or the volume of just the rock itself? I need a fluid that won't contaminate the rock, that won't get into any of the cracks. What to do? What to do? Every morning at 10 o'clock, all work stops. We all gather in the kitchen where we've got this industrial strength cappuccino machine, and we all get cappuccinos. And as I'm pouring sugar into the cappuccino, I'm saying, powders, sugar. Well, not sugar, actually. What we use are glass beads. You take a cup of known volume, it says 1/4 cup right on it, we actually measure it. Fill it with beads, shake it, scrape it, weigh it, you know the density of the beads. Dump out the beads. Put in the rock, fill up the rest of it with beads, shake it, scrape it, weigh it. The difference in the weights can be used to determine the density of the rock, and the beads don't get into the cracks. Then, you use this gizmo next door, which is a homemade gizmo that we got from a grad student who was no longer using it in Arizona. It's 2 tanks. You fill one tank with helium gas at 2 atmospheres. You put in your rock, and then you put in the plug hole at the other side, 1 atmosphere of helium. You measure the pressures really carefully. You open the valve, and they equalize. The bigger the volume of the rock, the higher the final pressure, because the rock is taking up some of the volume. The only thing you need to do is to have some calibration spheres, some things whose volume you actually know, because they're nice and regular, and you can use those to calibrate the system. So we went out and got carefully manufactured calibration spheres, numbered 1 to 16, and color-coded, solids and stripes. They work beautifully. Between these 2 volumes, you can compare what's the volume of just the outside or what's the volume of the rock without the cracks. And the difference is, what's the percentage of the rock that's made out of cracks? And you get a measure of physically how the rocks are put together. We can then compare these to the densities of the asteroids, and we find out that asteroids are not big rocks, but they're piles of rubble. If you wanted to blow one up, you don't send Bruce Willis out there, you know, it's not going to work. If you want to mine it, all you need is a spade and a bucket because it's nice and soft. If you want to deflect it, it basically, out of these measurements, we have a completely new understanding of how the asteroid belt evolved. But wait, there's more. Not only did I get to do that, but another number that turns out to be important is how much do these rocks heat up when you add a little bit of heat? Heat capacity is how much does the temperature rise for every bit of element of heat that you put in? Or alternately, how much does the temperature drop as you pull that heat out? How do you measure that? You take a flask with liquid nitrogen, drop the meteorite in. As it boils away, as you drop it in, the weight goes up. As it boils away, the weight goes back down because it's boiling off nitrogen until you get to the point where the rock is at liquid nitrogen temperature. You know how much the temperature has changed. You know how much extra nitrogen got boiled off. You now have a measure for the heat capacity of the rock. You can do it quickly. It doesn't destroy the rock. You can use it on an entire hand sample and not just a tiny bit like the commercial machines. And the best of all, you get to play with liquid nitrogen, which is great fun. These are the measurements that we're doing. Because I don't have to worry about getting a grant, I can do it. It takes years to go through the entire collection, 1,000 rocks. I've got years. I don't have to worry about tenure. I don't have to worry about having results in time to get my grant renewed. I can do what's sometimes called orphan science. Science that everybody would like to have done, but nobody can afford their career to do it. In addition, we're astronomers, so those telescopes that you saw on the roof of the Papal Palace, they're 75 years old, they're kind of ancient, and the light pollution around there has made them unusable. So 20 years ago, we went to Mount Graham, Arizona, located in pretty much the middle of nowhere, and we're part of an observatory building a number of telescopes. This was our telescope, the Advanced Technology Telescope, and I could talk for hours about this telescope. The cool thing is, you notice how steep the mirror is. It was formed by melting glass and then spinning it in an oven so it froze into the perfect parabolic shape you want to concentrate light. The guy who invented this procedure was named Roger Angel. So yes, the Pope's telescope is made by an angel. It's an F1 mirror, and with this telescope, I get to play with looking at the asteroids and the other objects in the outer solar system, like this guy. Forget that ugly galaxy in the front that's kind of in the way. We're interested in that little dot of light down at the bottom. When you look at it through 3 different colors, you can see its color, its brightness in red, and in green, and in blue. And it seems to be tricolored because it's moved from the time we shifted the filters. But from this, we can measure how fast it rotates, how irregular its shape is, and those things you can use to work out the shape and the density and the strength of the object itself. In this way, we can compare the asteroids with the meteorites. Every now and then, we do have a little bit of fun and take a pretty picture. This is one of mine. It's a pretty picture. An awful lot of astronomy is remembering to have fun. For the really faint, distant objects, even our telescope isn't big enough. And so you have to sometimes go to Hawaii. Life is tough, I know. Except that the place in Hawaii where the telescopes are is as far from the beach as you can get. The Keck 1 and Keck 2 telescopes are currently the largest in the world. They're made out of segmented mirrors that are 10 meters across. What's the advantage of having a big mirror? What does a telescope do? Everybody thinks a telescope makes tiny things look bigger, far away things look closer. For us, we use a telescope to make faint things brighter. Here's a 1970 image of a pretty random piece of the sky. And this is what the image looks like with the Keck telescope. You can see how having the bigger mirror allows you to see much fainter objects. The one problem with the Keck telescope is that it's at 14,000 feet, where there's like not a whole lot of air, and you're usually given one night, so you don't even have time to acclimate. Nowadays, instead of going to the telescope, you actually go to this little village that's a few miles away from the telescope, and there's a high-speed internet line, so that when you're working at 4,000 feet, communicating over a computer, astronomy, looking through a telescope. What could be more exciting? Here's a typical observing run. Here we are at 9 in the evening, looking at a bunch of computer screens. Here we are at midnight, looking at a bunch of computer screens. Only there's a bag from McDonald's, because there's a McDonald's just up the road from this building. Here we are at 3 in the morning. The bag of McDonald's is now empty. Later in the morning, 6 in the morning. That's astronomy. And you get to do that for 5 nights in a row. And then you've got 6 months of going back home with all of your data, trying to figure out, what was that little scratch there, and how can we get that out of the data? And how can we clean this up? And once I finally get the numbers out of how many photons actually hit that piece of the chip, I can work out the brightness and eventually try to get some science out of it. Most of the work of an astronomer is very tedious day-to-day work. And sometimes, when you're an astronomer, you're faced with a sky like this. Here we were in Hawaii, flown all the way from the United States continental part, the lower 48. We had one night. We got to this building, we could see it was cloudy. We called up at the top of the mountain, they say it's snowing there. They're not going to even open the telescope. We drew straws. One person got the short straw and stayed up all night just in case the weather improved, but it didn't. The other 2 of us just went to bed. And that morning, about 7 in the morning, I woke up and I realized it's Sunday morning. And I'm a good Catholic boy, but only a brother. You know, I can't say Mass. I can hear your confessions, but I can't forgive you. But I'll bet you, I say to myself, you know, if this town's got a McDonald's, it might have a Catholic church, too. So I get on the internet and find out, sure enough, they've got Mass at 8:30. And it's walking distance, because it's a small town. So I walk into the church. And it being Hawaii, it's full of people who are, you know, half of them there are tourists. And the priest gets up and he, do we have any visitors here today? And half the people put up their hand. Oh, and where are you from? And they say, from Ohio. Oh, welcome. And where are you from? Oh, you're from California. Great. Where are you from? Oh, we're from Illinois. Great. And I'm the last one called. He says, where are you from? And I stand up and I say, I'm an observer from the Vatican. Observing from the Vatican, actually, the guys who lived there got the joke because they knew about the observatory. It was all the visitors who looked really nervous. Observing from the Vatican has gotten me a lot of places I might not have gotten otherwise, including a childhood dream. I grew up in the Great Lakes. I love the snow and the cold. Thank you for this weather. I also love water. This is a beautiful frozen sea. This is Antarctica. This is a region called the Blue Ice Fields of Antarctica. We were an expedition of 6 people living in tents. This picture was taken at midnight, looking due south, looking into the wind. You may ask, what was I doing up at midnight outdoors looking due south? The wind always comes from the south. It slides down the Antarctic disk. And the rule is, if you're going to get your drinking water, you go upwind to chip some water. And if you're going to dispose of your drinking water after it's been drunk, you go downwind. And that's what I was doing up in the middle of the night. This is where we lived for 6 weeks. You can see the frozen food stored outside, the little weather station next to it, a bucket with ice that we chipped upwind, and behind the bucket there you see a shovel. Every morning, you would put on all your clothes, crawl out, start the skidoo, rock it back and forth, because it might have been frozen to the ice by then, drive downwind to a sastrugi, which is a wind-blown dune of snow, park the skidoo sideways, go downwind from it, dig a little hole, and hope you remembered the toilet paper. This is what, of course, the well-dressed astronomer wears in Antarctica. And we would go in skidoos back and forth across the ice until we found a rock sitting on the surface. Anything on that surface that's not ice is probably a meteorite. And in fact, the ice moves and concentrates it in these regions of blue ice. But we also took a view of one of the most glorious landscapes you're ever going to see on the face of the earth. When you're traveling and you see nothing but snow and ice, every other person you find is precious. And when you come home to see the tents on the horizon, you realize there are only 6 people in the world and you're one of them. We celebrated Thanksgiving and Christmas on the ice. Thanksgiving we had what we thought were going to be chicken pot pies and turned out to be chili rellenos, but that's okay. We made friends, friendship that has lasted to this day. One of my friends from this, Sarah Russell, I'm now godfather to her daughter. She took this picture. And it was a very spiritual sort of thing. O Lord, you have searched me and known me. You know where I sit down and when I rise up. You discern my thoughts from afar. Where can I go from your spirit, or where can I flee from your presence? If I take the wings of the morning and settle at the farthest limits of the sea, even there your hand shall lead me. If I say, surely the darkness shall cover me, and the light around me become night, even the darkness is not dark to you. Very true in Antarctica where the sun never sets. The night is bright as day, for darkness is as light to you. Psalm 139. This was as close as I have ever gotten to being on another planet. Now I mentioned that I loved ice and snow. My thesis at MIT was based on ice and snow. And so, a couple of years ago, when the authors, the editors of this book, this textbook on Europa, asked if I would be a co-author of the opening chapter, I was so delighted. I love Europa, the icy moon of Saturn. You probably know it in one of the Harry Potter stories. Harry Potter is trying to do his homework and Hermione says, "Harry, the surface of Europa is covered with ice, not mice." Your reaction is, "Oh, that's funny." My reaction is, "That's my thesis! Ice on Europa! I did that! Harry Potter is quoting me! Wow!" That's my thesis. It's on thermal history models of icy satellites. I actually wasn't the first one to say it was covered with ice. I was the first one to explain why it was covered with ice. That all the rocks probably have radioactive elements, and that means as they decay, the water is going to melt and it's going to form this liquid ocean under an ice shelf. And then I found out the chapter that they wanted me to write was the history chapter. The history of the study of Europa. Because my thesis was in 1975, and everything that I wrote about is now considered ancient history. 1975 was before Galileo got to, the Galileo probe got there, before the Voyager probe, before the Pioneer probe got, well, actually Pioneer had just passed when the thesis came out. So I wrote up the history of what we used to think Europa was like. Because in fact, it turns out that my models were all wrong. I underestimated the heat flow by a factor of 10, and I underestimated the sources of heat by a factor of 10, and the two errors canceled out. But, if I'm writing the history chapter, I had another question. You know, okay, before Galileo, before Voyager, before Pioneer, before the spacecraft got there, I was writing my thesis saying that they were going to be a mixture of rock and ice. How did I know they were made of ice if we'd never been there? You can actually find the spectrum of ice, and that had been done in 1971 when I was starting my thesis. But nobody was surprised it was ice because they were looking for ice because they expected ice to be there. Before we had spectra, before we had spacecraft, back in the days when the moons of Jupiter were nothing more than dots of light in a telescope, we knew they were made of ice. How did we know that? Who was the first person to realize that the moons of Jupiter were made of ice, not mice? That's a cool question. And I'm working at the Vatican. Which means, number one, I can waste a couple of months chasing that down, and my grant agency is not going to worry. And also, I happen to have my office right out that door to the left, across the hallway from one of the nicest libraries of astronomy, including that book there that the Pope is looking at, which is the Copernicus copy that we have. It's only a 3rd edition. It's not a 1st edition, but it's still not bad. We've got some wonderful old books. Well, I know enough about astronomy to kind of have an idea how you would know the moons of Jupiter are made of ice. There's 2 lines of evidence. One is, the moons are really bright compared to rock. Europa and the moon are roughly the same size. Actually, Europa's a little bit smaller. But where the moon reflects 12% of its light back to our telescopes, Europa reflects 65% of its light. So it's made out of something that's really shiny. How do we know that? Well, you can measure how much light compared to what light comes from a star. And if you know how big the moon is, and you know how much light is coming to you, and you know how much light is coming out there from the sun, you can do the calculation and say, okay, half the light is coming back to us, or 12% of the light is coming back to us. So in order for this to work, you have to be able to measure the brightness. You can do that with the naked eye. Just compare the moons to something in a telescope. And you have to know how big is the cross-section reflecting back at you. There's another way. My old friend density, mass divided by volume. So I have to know how big it is to get the volume. And I have to know the mass. How do you measure the mass of a moon? It turns out to be really hard. The motion of the moon tells you the mass of the planet it's orbiting, but it doesn't tell you the mass of the moon. Because a big moon and a small moon orbit at the same rate, just like a big rock and a small rock fall to the ground at the same rate. But Jupiter is a system of 4 moons, And back in 1803, this guy, Laplace, worked out how the mutual interactions can actually be used to come up with masses. And darn it, it worked. His numbers, compared to the modern numbers, are really good. They're good within 10%. In 1803, they knew that. How do you find volumes? They're just a little dot of light. You can't measure it in the telescope. But as the moons cross in front and behind each other, you can time how long it takes for one to overcome the other in what are called mutual events. And they were doing this in the 1840s. So by the 1840s, they knew how big they were, they knew how massive they were, they had all the information they needed to work out the density and to work out the brightness. So now it's just a matter of going into the library, looking up some books to see what do they say. And I found dozens and dozens of books that listed the masses and the radiuses, radii, of the moons of Jupiter. But I found some very strange things. In this particular book by Simon Newcomb, who incidentally was the model that Arthur Conan Doyle used for Professor Moriarty, he writes, "The light of the satellites varies to an extent that's difficult. It varies. Very violent changes constantly go." Wait a minute. I've looked at these moons all my life. They don't vary in brightness. But Simon Newcomb says they do. Everybody says they vary in brightness. What in the world is he talking about? Were they varying in brightness in the 19th century and they don't anymore? Very strange. Okay. I go through all the books and I see the lists of the masses and I see the lists of the sizes, and nobody bothers to divide the one by the other to come up with the density. It never occurs to anybody to do that calculation. You're measuring densities of Christmas presents if you want to know what the Christmas present is made of. But nobody thought of these places as places. They just thought of them as dots of light in the sky. There was an utter failure of imagination. I found exactly one book where the guy did the calculation. This book, Chambers. Here's his list of data. There are his masses. There are his densities. There are the numbers that he come up. You can't read that, so let me blow it up. He says, according to him, if water is a density of 1, then Europa has a density of 0.17. And I'm going, that's not right. In fact, that's wrong. In fact, that's not even wrong consistently. In fact, that doesn't even work with the numbers he himself uses. If I used his mass and his volume, those are the numbers I would come up with. Sometimes he's wrong by a factor of 8, other times wrong by a factor of 11, other times wrong by a factor of 4. He did the calculation, but he goofed it up. And what's more, he never did the thing that we tell all of our physics students to do. After you do the calculation, step back and say, does this make sense? What in nature is 1/10 the density of water? You know, besides balsa wood, basically nothing. It doesn't happen in nature. This should have been a big red flag. But he makes this calculation and then never uses it. Never even guesses what these moons could be made of to have such a weird density. An utter failure of imagination. Finally, at the end of the 19th century, this guy, Pickering, working at the Harvard College Observatory, that used to be my office, comes up with his table, and by golly, he comes up with densities and brightnesses that are reasonable. Finally, he's got the numbers. And what's more, he's got a new way of measuring the brightness. He looks into the telescope, and instead of just looking at the Europa and then going to look at a star, he has a little tube that looks just at Europa, and he can make it lighter or darker to measure it. And he says, many astronomers thought the light of the satellites were variable, but I don't see that in the present measurements. Bum, 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 bum. Before him, people were using the naked eye. Where do you see Europa? Next to Jupiter. Anybody here seen Jupiter in a telescope? It's really bright, so it makes your eye shut down. So naturally, every time Europa is close to Jupiter, it looks fainter, because in fact it's really that you're being blinded by Jupiter. And all of these professional astronomers for 50 years hadn't thought of that. And they had these wild theories that these moons must be flat as a pancake and tumbling so that sometimes they're bright and sometimes they're dim, when in fact it was just bad data. In no case have I been able to perceive any marked change in their relative brightness. So you don't need flat moons anymore. Hey, he's almost there. He's almost got it. It will be noted that the densities are extremely small for solid bodies. You know, they're much less than rock. Either they're enveloped in clouds, which doesn't seem likely, or their density and brightness are what we expect if they were made of loose heaps of white sand. So close! Why does he want white sand? Because if they're made of sand, then that explains why they're so flat when they spin. Except he just proved they don't have to be flat. But he forgot that. It's not until 1923 that Sir Jeffreys, writing a paper about the moons, actually writing a paper about Jupiter, he wants to know what's Jupiter made out of. He says Jupiter must be made out of ice because, after all, the moons are made out of ice. Everybody knows that. If you've got these moons made of ice, and finally Jeffreys realizes it, and you've got this ocean, and you've got this icy crust, and you've got a mind that's wasted way too much time reading science fiction, you might write in your thesis as the very last paragraph, the temperatures of the interiors, and especially the silicate layers, the rocky stuff where the liquid is percolating, the possibility exists of simple organic chemistry taking place between the water and the rock. However, we stop short of postulating life in these mantles. We leave such to others more experienced than ourselves in such speculations. Boy, was I a snotty kid back then. I was, of course, thinking of Carl Sagan, who was always looking for life. And that was a not at all subtle reference. Dig at him. So you see, I am not the first person to predict life in the oceans of Europa. I am the first person to specifically not predict life in the oceans of Europa. I gave this as my very first paper in May of 1975 at a big meeting, and the chair of the session was none other than Carl Sagan himself. And so I go up to Carl Sagan and say, I've got this great idea, blah, 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 life in the oceans. And Carl goes, how thick is that icy crust? A couple of miles. Light can't get through it. Life depends on a source of energy, on sunlight. It's going to be dark in the oceans. It's impossible for life to be there. And I go, oh. Gee, I wonder if you could get life from the volcanoes. Nah. 4 years later, we find life due to the volcanoes in the dark parts of the oceans on Earth. And a few years after that, somebody else writes the paper about life in Europa, including Steve Squires, who was a grad student of Carl Sagan's. But this got me thinking. Imagine, if you will, that you're an intelligent tuna swimming in the ocean of Europa. As far as you know, the center of your universe is this round, rocky bottom, and there are crystalline spheres of ice above you. And there is no way that you would even be aware of a universe above you. All of your science would tell you that you are living in this geocentric or Europa-centric universe. Until one day, something cracks the surface, and you get splashed up into space, and you discover it's full of stars. This is not Europa. This is another moon also made of ice called Enceladus, which actually has cracks, which actually has water spewing out of the surface. I entitled this talk, Brother Astronomer, Adventures of a Vatican Scientist. But I hope you realize the talk actually isn't about me. It's about the doing of the science, not the factoids, the actual activity of being a scientist, the adventures. The adventures involve imagination. The adventures involve recognizing what's home and what isn't. The failure of the people who didn't understand what Europa was made out of was a failure of imagination. They couldn't think of Europa as a place. It wasn't until we could think of it as a place that we could think of it as a place made of stuff and try to guess what that stuff would be. The adventure of going to Antarctica is what allowed you to deal with the hardships of living for 6 weeks in a tent, with no showers, incidentally. Got to be good friends. The adventure is what makes you want to take pretty pictures with a telescope. But also, it's the adventure that allows you to spend the day after day after day of tedious work measuring each spot on your images, each image that you took, to try to work out the light curve and the color and ultimately the composition. Work that at the end of the day you don't feel like you got very much to show for it, but at the end of a year you've got a story you can tell your friends. Astronomy is an adventure. Science is an adventure. And one of the important questions to ask is, why do we do it? Why do we do it when people are starving in the world? Why do we do it when sometimes I'm starved for attention or I'm starved for chocolate? We do it because we are answering a call from outside ourselves, to pull ourselves outside ourselves, to ask more than what's for lunch. We do it because we are being called by the transcendent, which is to say we are answering a call from God, a call to get to know God. I'll end with one short story. Some of the students may have heard me tell this earlier. When I was a little boy, I remember one summer Sunday afternoon when it was pouring rain. We were at the summer cottage on the shores of Lake Huron. We're in the front porch, which is all enclosed, so we're not getting wet, but we can't go out. And I remember my mom coming up with a deck of cards and dealing out and playing rummy. And of course, she's a grown-up, I'm a kid, she's gonna beat me. Winning the game wasn't the point. The point of the game was that this is how she could show me that she loved me. You can't tell a 10-year-old kid, son, I love you, because you got a kid's going to go, oh, Mom. But this was better than anything she could say. When I do science, I'm solving a puzzle posed by a wonderful puzzle maker who I'm sure is having a great time watching me stumble through the puzzle and celebrating with me that moment when I got it! Because that feeling of joy you get when the graph finally fits is much like that feeling of joy I get sometimes in a moment of prayer. It's God playing with me. It's God telling me he loves me. If that's why you do the science, then you deal with the tedium for the marvelous reward. And if that's why you do the science, then you're dedicated to truth, which is the God I believe in. Thank you very much.